Ever looked up at the night sky and felt a shiver thinking about black holes? These cosmic monsters swallowing everything, even light itself. For the longest time, we thought they were the universe's ultimate prisons. Once you're in, there's no coming out. Game over, right? Well, what if I told you that's not the whole story? What if black holes aren't eternal? What if they have a life, and more importantly, a death? This changes everything we thought we knew. The idea comes from one of the greatest minds of our time, Stephen Hawking. He looked at the seemingly perfect, inescapable nature of a black hole and found a crack in its armor. He realized that even these gravitational titans have to play by the universe's rules. Specifically, the weird and wonderful rules of quantum mechanics. So, how does a black hole die? It's not a sudden explosion, but a slow, graceful fade. It glows. Yes, you heard that right. A black hole, the very definition of darkness, actually emits a faint glow. This isn't light from inside struggling to get out. It's something far more bizarre, born right at the edge of the black hole, at the point of no return we call the event horizon. This faint glow is called Hawking radiation. To understand this, we need to take a quick dip into the quantum world. In the seemingly empty vacuum of space, things aren't actually empty. There's a constant fizz of activity where pairs of virtual particles pop into existence. One is a particle, and the other is its antimatter twin, an antiparticle. Normally they appear, look at each other, and instantly annihilate, disappearing back into nothingness. It's a cosmic dance happening everywhere, all the time. But what happens if this dance occurs right on the edge of a black hole's event horizon? Picture it. A particle-antiparticle pair pops into existence. One falls into the black hole, but its partner, just by chance, is on the outside and manages to escape. From our perspective far away, it looks like the black hole just spat out a particle. This escaping particle is real, and it carries energy away with it. Now, where does this energy come from? There's no free lunch in the universe. The energy for this newly freed particle is stolen directly from the black hole's mass. Think of Einstein's famous equation, E or mc2. Mass and energy are two sides of the same coin. By emitting a particle, the black hole gives away a tiny bit of its energy, which means it loses a tiny bit of its mass. So, the black hole is glowing, emitting particles, losing energy, and therefore, it's shrinking. This process is incredibly, unbelievably slow. For a black hole the mass of our sun, it would take longer than the current age of the universe to evaporate even a tiny fraction. But for smaller black holes, the process is faster. The smaller it gets, the hotter it glows, and the faster it evaporates. This slow fade continues over eons. The black hole gets smaller and smaller, lighter and lighter, until it reaches the very end of its life. In its final moments, what was once a supermassive giant becomes a microscopic speck, radiating away its last bit of mass in a final, brilliant flash of energy. And then, it's gone. The space-time warp it created smooths out, as if it were never there. This raises a mind-bending question, a puzzle that has fascinated physicists for decades. What happened to all the stuff that fell in? Every star, every planet, every bit of matter that crossed the event horizon over billions of years. Does it just vanish from existence? That would violate one of the most fundamental laws of physics, that information can't be destroyed. Information, in physics, is essentially the unique identity of every particle. Its position, its velocity, its spin. It's the universe's data log. The idea that this information could be wiped out forever inside a black hole created a paradox, a deep conflict between our understanding of gravity and quantum mechanics. This is known as the black hole information paradox. So when the black hole evaporates, where does that information go? Does it get scrambled and returned to the universe in the random particles of Hawking radiation? Or is it stored somewhere we can't yet comprehend? One popular idea is the holographic principle, which suggests that all the information about what fell into the black hole is actually encoded on its two-dimensional event horizon, like a cosmic hard drive. As the black hole evaporates, this information is somehow imprinted onto the outgoing radiation, returning it to the universe. It might be scrambled beyond recognition, like trying to reconstruct a book from the smoke of its burning pages. But in principle, it's still there. The universe's story, it seems, is never truly lost. So, The next time you think of a black hole, don't just see it as a prison. See it as a long-term cosmic recycling plant. It takes matter and energy, holds onto it for an unimaginably long time, and then slowly releases it back into the cosmos. It's a testament to the fact that in our universe, nothing is truly forever. Not even the darkest objects we can imagine. Everything is part of a grand, ongoing cycle of creation and transformation. Thank you so much for joining me on this journey to the edge of space and time. It's a huge topic, and we've only scratched the surface. Until next time, keep looking up.